Hello math friends, this is AP Calculus section 2.10 notes. Today we are going to be focusing on working backwards. We've been talking for a while now about the relationships between a function and its derivative and how if we know things about a function, we can use them to make determinations about the derivative of the function. Today, we're going to be working backwards. What if we know things about the derivative? How can we use information about the derivative to infer things about the function that it was derived from? So the first thing that we want to think about is increasing and decreasing. We have talked about how if our function is increasing, the derivative is above 0, and if our function is decreasing, the derivative is below 0. So if we think in the other direction, if our derivative is positive or above the x-axis, that means that our original function was increasing on that interval. If our derivative is negative or below the x-axis, then we know that our original function f was decreasing on that interval. And we also know that anywhere that our derivative crosses the x-axis, our original function f had a horizontal tangent, a zero slope, or a local max or min, right? We think of that as a turning point on our curve. In our first example today, the graph of a derivative f prime of a function f is shown. So again, focus on the fact that we are looking at the graph of our function's derivative, not of the function itself. But they're asking us questions about the function, not about the derivative. Part A says, on what intervals is f increasing, and on what intervals is f decreasing? So let's begin with increasing. We have a graph of the derivative of our function. We know that our function would be increasing anywhere where our derivative is positive. So right here, and right here, and right here are going to be the places where our function is positive. And if we are trying to estimate values along the x-axis, which is always what we're doing when we're giving intervals. I would probably say that our function is increasing, and we're going to go from left to right. On our x-axis, it looks like that is about negative 1.4 right here is what I'm talking about. That point right there is about negative 1.4 where that blue dot lines up with. So I would say my function is increasing from negative 1.4 up to right here, which is x equals negative 1. And then it's increasing again, so union from here to here, it's increasing. So that's from 0 to 1 on my x-axis. And then it's increasing again from 2 to this point right here, which is a little less than 2.5, so we'll go with 2.4. So from 2 to 2.4. And again, this is because f of x, or f prime of x, is above the x-axis. Well then, where is f of x going to be decreasing? That's going to be happening at the locations where our derivative is negative. So these two parts that I'm highlighting in red. On the x-axis, it's going to be decreasing from negative 1 to 0, and then again from 1 to 2. And again, decreasing because f prime of x is below the x-axis. Part B asks us, at what value, x values, does f have a local maximum or a local minimum? Well, remember, if f of x has a local max or min, these are locations where slope equals 0. And on f prime of x, these are x-intercepts. That's a very important relationship to understand. So those locations are going to be x equals -1, 0, +1, and +2. All right, then part C says, if f of 0 equals 0, sketch a possible graph of the function f. So what I'm going to do is I'm going to sketch a coordinate plane right below my f prime of x, and I'm going to try to line up my f of x with the features of f prime of x. So I'm going to put my x-axis scale in the same locations here. All right, so I know that my function has to be increasing from about -1.4 to about -1 on the x-axis, and then at -1, I know that I have a turning point. So I assume that my function is going to look something like this to begin with, and then I have a 0 slope here, or a turning point. But then I know that I'm decreasing from x equals -1 to x equals 0 until I have another turning point right here. These are 0 slope locations. Then I am increasing from x equals 0 to x equals 1, because I'm above the x-axis, where I have another turning point. And then I am decreasing from x equals 1 to x equals 2 here, where I have another turning point. And then I am increasing from that point on. All right, now one question that you may have in your mind here is, how did I know how high to go on my y-axis? That's a great question. And exact heights of turning points cannot be determined with the information that we have. The only information that we were given about our function f is that f of 0 equals 0. So the only point that I knew for sure was this point right here. I knew that my function f had to pass through that point. Any of the other local turning points or local maxes and mins could have been at different heights than I drew them at. However, the general shape of the function f of x should follow the shape of the graph that I had drawn. Please note that all of my local maxes and mins align with the x-intercepts on f prime of x, where f prime of x is above the x-axis, f of x is increasing, where f prime of x is below the x-axis, f of x is decreasing. So at this point right here, this is the best that we can do for part C of example 1. Example 2 says to use the given graph of the function f to estimate the intervals on which the derivative f prime is increasing or decreasing. Begin by sketching a graph of f prime. All right, well, the first thing that we want to think about if we want to sketch a graph of the derivative is we want to look at locations where our slope is 0 on our original function. And so we have a 0 slope here, a 0 slope here, and a 0 slope here. So that we know that on our derivative, these are going to be locations where our derivative is going to cross the x-axis. I'm just trying to line those up the best I can with the turning points there. This isn't an exact science, it's approximate. And I know that on my original function f of x, from about -2 up to about x equals 1, my function is increasing, right? The graph of f of x, the graph of f of x is going up from left to right, increasing, which means that my derivative needs to be above the x-axis. So my derivative has to come down and do something like that. Then I know from about x equals 1 to about x equals 3, on my original function f of x, I am decreasing, because from left to right, the graph is going down. When I'm decreasing, I know that my derivative must live below the x-axis. So between x equals 1 and x equals 3, I have to dip below the x-axis. Then, back to my original function f of x, from x equals 3 to about x equals, I don't know, 6.75 or so, I am once again increasing. So I know that my graph needs to be, my derivative graph needs to be above the x-axis. However, it needs to cross the x-axis again where I put that third x-intercept. So I'm going to have some sort of a hump above the x-axis between x equals 3 and about x equals 6.75. So something like this. And then finally, on back to my graph of f of x, I am decreasing from x equals 6.75 all the way to about x equals 9. So on my derivative graph, I am going to be below the x-axis in those locations. All right, so I think we've successfully sketched a picture of what f prime of x, and again this is f prime of x, what f prime of x could look like. So now they want us to estimate where is f prime of x increasing. Okay, well, f prime of x is increasing from, let's see here, if you take a look at the graph, f of x is increasing from here to here, right? The graph is going up from left to right. So it is increasing from about x equals 2 to x equals 5. And then f prime of x is decreasing in two places. It's decreasing here, and then it's decreasing here. So I would say that the intervals on which it is decreasing are from -2 to +2, and from 5 to, the graph goes to about 9 on the x-axis. So from 5 to 9. Now there's one more thing that I would like to point out, and this is a relationship that we have not actually learned yet, but it's coming soon. So it's always good to talk about things as soon as we are able to. And what I want to talk about is something called an inflection point on f of x. An inflection point on f of x is a point where the graph changes from concave up to concave down or vice versa. And so inflection points typically happen between turning points. We have an inflection point on f of x right there, and we have an inflection point on f of x about right there, okay? Notice that concavity-wise, I could say that my function is concave down, and then it switches to what we would call concave up, and then it switches again to concave down, okay? And the reason that we care about inflection points is when you look at where the inflection point on f of x lines up with f prime of x, notice that inflection points on my original function become turning points on my derivative function. So let's write that down. Note that inflection points, and I abbreviate those as IP, on f of x, that's our parent function or our original function, are turning points, okay, local maxes or mins. That's what a turning point is, local maxes or mins on my derivative f prime of x. Okay, so again, not something we've learned yet, but something that is going to be introduced later in this lesson, but this graph was an excellent opportunity to point out the inflection points on f of x becoming turning points on f prime of x. In example 3, they've given us graphs of two functions, f of x and f prime of x, but they don't tell us which is which. So our job is to determine which function is f and which function is its derivative f prime. And then after we figure that out, they're asking us which value is bigger, f prime of -1 or f prime prime, so second derivative of +1. So we'll do that after we figure out which graph is which. So when we try to determine which graph is the original function, or f of x, and which graph is its derivative, f prime of x, the things that we're looking for are zero slopes on f of x becoming x-intercepts on f prime of x, and we're looking for where f of x is increasing, f prime is positive, and where f of x is decreasing, f prime is negative. So I am looking for locations, and of course they've done an excellent job here of making sure that all turning points and x-intercepts line up both ways, which makes this a little bit trickier. So instead, what we need to look at is increasing and decreasing. If I start from left to right and I look at the blue graph first, I would say that the blue graph is increasing from its starting point, which I would say is right here, up to here. So that would mean that if the blue graph was f of x, that its derivative should be above the x-axis that whole time. But notice that the pink graph is not above the x-axis that whole time. So that tells us that the relationship must go the other way. The blue graph cannot be f of x. The pink graph must be f of x. So let's check that. If I look at where the pink graph is increasing, just to verify that I am correct in my thinking, the pink graph appears to be increasing from here to here, and the blue graph is above 0 from there to there. And then the pink graph begins to decrease from here to here, and my blue graph is below 0 from there to there. And then again, over here you could see we've got decreasing and decreasing. And then we go back to increasing again. My pink graph, which is my f of x, is increasing from here to here. And my blue graph is above 0 from there to there. And then finally my pink graph is decreasing from here to here. And my blue graph is below 0 from there to there. So I can say that the pink graph, I know I've recolored everything now, but the pink graph is definitely our f of x. And the blue graph is our f prime of x. Okay, and now that we've made that decision, they're asking us to categorize f prime of -1 and f prime prime of +1. And I know you're thinking, well, we don't even have a graph of f prime prime. We'll get to that in a second. First, let's think about f prime of -1. We do have a graph of f prime of x. And f prime of -1, f prime of -1 is right here, okay? So what do we know? We know f prime of -1 is a positive value. Well, if we had a graph of f prime prime, we know that wherever f prime is increasing, f prime prime would be above the x-axis. Wherever f prime is decreasing, f prime prime would be below. And wherever we have a local max or min on f prime, a zero slope on f prime, its derivative f prime prime would have a value of 0. Well, at x equals 1, f prime of x is right here, right? F prime of x has a local max at x equals 1. It has a 0 slope there. So that tells me that f prime prime of 1 would have an x-intercept at x equals 1. So the value of f prime prime of 1 would be 0. So now we can order these. We can say that f prime of -1, which is a positive value, would have to be greater than f prime prime of 0. All right, in the second graph, we are starting over completely, okay? And so once again, we need to think about increasing and decreasing, okay? So if we start with the pink graph, all right, so let's just look at the pink graph. On the pink graph, from its start up to about here, we are decreasing. So we should expect then, if the blue graph were its derivative, we should expect it to be below 0, which it is. But then the pink graph starts increasing. So we should expect the derivative to be above 0. But, if this is the derivative, it's not above 0, it's below 0. So what that tells us is that the pink graph can't be f of x. The blue graph has to be f of x. So let's go ahead and let's verify that that's true. If the blue graph is f of x, okay, then I should be, let's see, from its start to about here, it's increasing. My derivative should be above 0, which it is. And then my blue graph starts to decrease just for a little bit from there to there. And my pink graph, that same distance along the x-axis, is below 0. And then once again, my function f of x, my blue graph, is increasing from here to here. And its derivative is above 0. So you can see how this is matching up, right? And then my f of x is decreasing, and the derivative is below 0. And then finally, my f of x is increasing, and its derivative is above 0. All right, so based on that information, the blue graph in this situation has to be our f of x. So this graph right here has to be f of x. And the pink graph has to be f prime of x. So this one has to be f prime of x. All right, and the blue one, let's color code that for you, has to be f of x. All right, so now that we've made that determination, let's talk about f prime of -1 and f prime prime of +1 for this picture? Well, f prime of x is our red graph. So f prime of -1, f prime of -1 is right there. So we know that f prime of -1 is a negative value, right? We don't know what, but we know it's below the 0, so it's a negative value. It's below the x-axis. So let's think about f prime prime of +1. So here's +1 right here, right? And f prime of x is the curve that I colored with red. So if f prime of x has a turning point when x equals 1, that tells us that the derivative of f prime, which would be f prime prime, is going to have an x-intercept, or the value of f prime prime of 1 would be 0. So if I wanted to order these, 0 is bigger than a negative number. So I would say f prime prime of 1 in this case is going to be greater than f prime of -1. Next, we get to talk about what I had alluded to before, which is concavity and inflection points. So if we have a second derivative graph, if our second derivative, f prime prime of x, is greater than 0, is positive, is living above the x-axis, that tells us that our original function f of x is concave up on that interval. If our second derivative is negative or below the x-axis, that tells us that f is concave down on that interval. And a point where our curve f of x changes its direction of concavity is called an inflection point. So example 4 is kind of interesting. They say sketch a graph of the function that satisfies all of the given conditions. All right, so we have some information about f prime, and we have some information about f prime prime. They are asking us to sketch a graph of f, all right? So I have some advice for you as far as this process is concerned, sort of an order to do this in, if you will. So the first thing that I would recommend after you make your coordinate plane is you're going to sketch your increasing or your decreasing segments. Second step is to draw your zero slopes, which are your turning points. The third thing you're going to do is you're going to sketch the curve. And then the fourth thing that you're going to do is you're going to verify that your concavity matches the information that you have and the graph that you've drawn. Okay, so now that we have that sort of to-do list, let's take a look at the information that they've given us and what it tells us. Okay, now remember, we are trying to draw a graph of f of x. So knowing that, if they tell us f prime of 0 equals f prime of 2 equals f prime of 4 equals 0, anywhere that our derivative is equal to 0, we know f of x has a turning point. So this first bit of information says f of x has a turning point or a 0 slope because f prime of x is 0 in those locations. Our second bit of information says f prime of x is greater than 0, so above the x-axis, derivative is positive, if x is less than 0 or between 2 and 4. So this tells us, if our derivative is positive, this tells us where our function is increasing. So this information is where f of x is increasing. The next piece of information is that f of x is, or f prime of x is negative or below the x-axis between x equals 0 and 2 or when x is greater than 4. So again, if the derivative is negative, this tells us where our original function f of x is decreasing. And then finally, we have information about concavity. F prime prime, our second derivative, is greater than 0. So second derivative is positive between x values of 1 and 3. That tells us right here that f of x is concave up. Second derivative is positive, f of x is concave up. Then second derivative is less than 0 or negative if x is less than 1 or if x is greater than 3. So this tells us where f of x is concave down. All right, we've figured out what the information they gave us is telling us. We have sort of our order of jobs here. So the next thing to do is to sketch our coordinate plane and begin our graph. And when I look at the information that they give me, the highest x values they talk about are when x is 4. So I just went out to positive 5, negative 5. And I don't even really need to put any y values on the graph because, as we talked about earlier, the heights of our turning points are somewhat arbitrary unless we have more detailed information. Okay? So now I'm going to follow the instructions that I wrote down. And the first thing is to sketch the increasing and decreasing segments. So if you have a highlighter or like a yellow pen or something, that becomes useful. I know that the function changes from increasing to decreasing at 0, at 2, and at 4 based on this information right here that they gave me. So here's x equals 0, here's x equals 2, and here is x equals 4. And I know that when x is less than 0 or between 2 and 4, my function is increasing. So I know I'm going to be increasing here, and I know I'm going to be increasing here. And I know that I'm decreasing if x is between 0 and 2 or if x is greater than 4. So that's what I mean by sketching your increasing and decreasing segments. Then the next thing is to draw the zero slopes or the turning points. And again, the heights that you draw these in are not that critical, right? We're just looking for the turning points being at the correct x value. So I know that I have turning points at 0, at 2, and at 4, which makes sense because those are where my dotted lines are. So if I'm supposed to be increasing when x is less than 0 up until 0, that means that I'm going to put my turning point above the x-axis somewhere. So I'll put a turning point right here. And then I know I have another turning point at x equals 2, and I have to be decreasing from 0 to 2, so my turning point has to be down. And then my final, or my third turning point, again, at x equals 4, has to be up somewhere. Okay, so I've got my increasing, decreasing segments. I've drawn my zero slope or my turning points. And so now I need to sketch my curve, and then I can adjust it if I need to account for the concavity information that they gave me. Because I know that my concavity is changing at 1 and at 3. So that's kind of where I need to have that inflection point as I draw my curve. So if you'd like, you could maybe put a little dash in here that we know that that's where our inflection points are going to lie, and that'll kind of help us with the curvature of our graph as we draw it. All right, so I'm ready to take a guess here at what f of x might look like. I know that f of x is increasing until here. Now it has a turning point, and I know that it switches from concave down to concave up, so I have this inflection point right here. And then I have another turning point, and I'm still concave up until here. Those aren't necessarily right on the x-axis, but that's where I'm drawing them. And then I switch to concave down again, and then my graph stays concave down. Okay, so here is an approximate guess at what my function f of x could look like based on all of the information that I was given for example 4. Since we have been talking today in this lesson about how if we have f prime of x, or information about f prime or f prime prime, that tells us information about f of x. Well, that has a name in calculus, and we call that the antiderivative. So sometimes we're given some function, and they call this function f, and they want us to use that to go backwards and say, well, let's say f was a derivative of something. What could that something have been? And so that name that we give that something that f could have come from, or f could have been derived from, we call an antiderivative. So here's a new definition for us today. Antiderivatives. If we are given a function f, sometimes we're asked to find a function big F whose derivative is little f. If such a function exists, we call this an antiderivative of the function f. So on your paper here, this first curve, your book calls f of x. And then the second curve, your book calls capital F of x. So what you need to be thinking about is that little f of x is like the derivative. And big F of x is the possible antiderivative. And I use the word possible because there are many possible antiderivatives that could match a graph f of x. And the thing that defines which antiderivative is the correct one is the y-intercept, or the location where the exact graph crosses the y-axis. And if you look at these pictures here in this box, notice that they all have different specified initial values. So in the last problem that we just completed, I said that the graph that we made, and I'm talking about this graph right here, the graph that we made is a possible graph of f of x. And I didn't put any scaling on my y-axis because I didn't know how high those turning points or how low those turning points would go. And that's because I didn't have enough information about the antiderivative, or the f of x, capital F of x, that I was creating here. And that's a common problem when we think about calculus. They have to give us some sort of initial value and say, this point lives on your antiderivative. And then you have a better idea of what your function would look like based on that information. So understand that there are many possible antiderivatives that could satisfy a given function, and you only know which one is the correct one if they give you enough information about points that lie on your antiderivative curve. Our last examples, they give us a function in example 5 of f. F is the pink graph here, so on your paper you might want to color code that. Here is f of x. And they want us to determine which graph is a possible antiderivative and why. So only one of A, B, or C is the antiderivative for f. So the easiest way to do that is to look at the slopes, okay? So if we think about our graph of f, and we think about how we're looking for the antiderivative, remember that if we're looking for the antiderivative, then that means that f is the derivative. What do we know about derivatives? Well, we know that where the derivative is above the x-axis, so on my curve, where is my graph above the x-axis? From its start to about here. My derivative has to be increasing. Well, if I look at graphs A, B, and C, it looks like A and C are both increasing, but it looks like B is decreasing. So right away I can say B is out. B cannot be the antiderivative of f. All right, so now let's look more carefully. The point where my graph f changes from being above the x-axis to being below the x-axis is right there where I just put that dot. So that means that that is the point where my antiderivative should change from increasing to decreasing. Well, if you look at graph C continues to increase the whole time. So that tells me that graph C also is out. Graph C cannot be my antiderivative. So the only graph that's left is graph A. Graph A has to be the antiderivative of f. So let's write that down. Graph A is the antiderivative for f. And why is that? Well, we could say because graph A, its slope is increasing, then 0, and it's 0, or we have a 0 slope when f changes from above the x-axis to below the x-axis, right? Then it begins decreasing. Okay, so that's how we determined that graph A was kind of the last graph standing and had to be the antiderivative of graph f. Example 6, the graph of a function is shown. It says make a rough sketch of an antiderivative f given that f of 0 equals 0. Okay, so they've given us that initial condition. We know that our antiderivative has to contain the point 0, 0. So let's kind of work backwards the way that we sketched our graph back in example 4. The first thing I'm going to do is I'm going to sketch in my segments or my little yellow lines where I know that my function is increasing and decreasing. So I have to think of f of x as being a derivative of the function I'm trying to sketch. So think of it as being f prime, really, right? So my f of x is below the x-axis from 0 to 2. So that tells me that from 0 to 2, the graph that I'm going to draw is going to be decreasing. And then f of x is above the x-axis from 2 to 3. So I know that my graph will be increasing. And then once again, all the way kind of up to the end here, my graph is below the x-axis. So I know that my antiderivative will be decreasing. And then I look at, well, where does my f of x, my given graph, which is the derivative of the graph I'm trying to draw, where does that cross the x-axis? Because I know that those are going to be zero slopes or turning points on my antiderivative. So right here, I'm going to have a turning point. Right here, I'm going to have a turning point. And it's going to kind of, as you can see, it's sort of leveling off. So it's sort of going to level off over there. All right, so if I'm going to be starting at 0, 0, because that was a point on my curve, and then I am going to be decreasing, that means that my graph has to be dropping down because I have to have a zero slope here. Wherever my f of x had an x-intercept, my capital F, my antiderivative, has to have a turning point. So I would say that I have to be doing something like this. Then I know that my graph is going to be increasing. I don't know exactly how high it goes, but I know it's going to be increasing until it has another turning point. So I'm just going to draw it like that. And then I know that I am going to be decreasing again until I sort of level off like that. Okay? So here is my guess at what the antiderivative capital F might look like for this function f of x that I am given. Now let's take a look at a couple of other features of the graph and see if things that we've learned about so far make sense. We've already kind of used the above 0, below 0 on f of x means increasing, decreasing on capital F. We already know that the x-intercepts on little f are the turning points on capital F. The other thing is our inflection points, those changes in concavity that we learned about today. Well, I kind of have an inflection point right here on my capital F, and notice that that is a turning point right here on its derivative f of x. And again, I have an inflection point about right here, which lines up with a turning point on little f of x. And at some point about right here, I have another turning point or a change in concavity, which again lines up with a turning point on little f of x. So just to review, and again, here's just kind of a summary of information that you might want to write down. X-intercepts on f of x are turning points on the antiderivative big F of x. Turning points on little f of x are inflection points, are IPs, on big F of x. Okay, the concavity switches at those locations. And then again, our increasing and decreasing. When little f of x is less than 0, big F of x is decreasing. And when little f of x is greater than 0, big F of x is increasing. So just kind of a summary of what's going on with those two graphs. Capital F being the antiderivative of little f.